Hello. In this video, we're going to have a look at deMoivre's theorem, which is useful for helping us figure out the powers of complex numbers. So at its heart, deMoivre's theorem says that for all real exponents, so for all real values of n, r cis theta, so remember that is r cos theta plus r sine theta I, so this is a Cartesian or rectangular form of this complex number, raised to the power of n. Oops, there's a typo in this theorem here. Let's fix that. There should be an n there. That's kind of critical. That we can actually evaluate this much more easily than having to use a binomial expansion, as we would have to do if all we had was this Cartesian or rectangular form. This is going to be r to the power of n cos n theta plus r to the power of n sine n theta I. That would be the imaginary part of it. So remember, that's what that cis notation means. So the proof of this is actually kind of a sketchy proof for now because it rests on an infirm foundation, because as far as the sequencing of this course goes, we have not yet actually proved that r cis theta is equivalent to r e to the power of theta I. That proof will come later in the Math 35 course, at which point this proof will then be complete. But for the proof of deMoivre's theorem, which is actually quite trivial when we know this property, we are going to assume that this is a property we already know. So what that means then is that if I have this raised to the power of n, so r cis theta to the power of n, this is going to be the same as r e to the power of theta I raised to the power of n, which now, because I don't have an addition or subtraction inside of those brackets, is a simple application of exponent rules. So that's r to the power of n, e to the power of n theta I. But then we simply reverse the conversion into polar form, where r to the power of n is the new modulus. So this is equal to r to the power of n, and then cis and theta is the new argument, and theta. So that's it. That's the proof of deMoivre's theorem if we already have established that this polar form is equivalent to the rectangular or cis form, which, as I said, that's a little bit of a shaky foundation for now, but we will prove it once we have learned some Taylor polynomials. Now, what this can be useful for is finding powers of complex numbers. So if, for example, I have a square root, which is simply -1 plus root 3i to the power of 1/2, to find a sort of a better form, a simplified form, a Cartesian form of this square root, I'm going to initially have to convert it into polar form. So I need the modulus and the argument. So remember, the modulus of the argument is simply going to be the square root of -1 squared plus root 3 squared. So 2 is the r value here. And then if I want the argument, what I'm going to do is I'm going to factor that 2. So I'm considering -1 plus root 3i. But I want to actually factor out that 2. So that's 2 times -1/2 plus root 3 over 2i. Because now what I'm seeing is the cos theta and sine theta. So -1 is the cosine of theta, and root 3 over 2 is the sine of theta, which means if the cosine is negative and the sine is positive, I'm dealing with an angle in the second quadrant. And since the cosine is -1/2 and the sine is root 3 over 2, we're dealing with 2 pi over 3. So that is the argument here. So what this now means is that this root that I'm looking for is equivalent to 2 cis 2 pi over 3 to the power of 1/2, which is 2 to the power of 1/2. Cis 2 pi over 3 times 1/2 is simply pi over 3. I'll make that a little nicer. Cis pi over 3. Or in other words, since I was given this number in rectangular form, I'm going to convert it back to a rectangular form. So I have root 2 times the cosine of pi over 3 plus I sine of pi over 3. And the cosine of pi over 3 is 1/2. The sine of pi over 3 is root 3 over 2. And when I distribute out that root 2, which you don't technically have to do, but I get root 2 over 2 plus root 6 over 2I is the square root of that original one in rectangular form.